onward. He is still actively working there. And awards and recognitions, the list is very large. However, I will include only the some of them. The Distinguished Fellow of International Engineering and Technology Institute 2020. He got Gold Medal Lifetime Achievement in Chemical Research Society of India 2019. Distinguished Material Scientist of the Year Award in 2011. And Honorary Doctor of Science, Purdue University, Indiana, USA 2010. Padma Shri, Civilian Honor awarded by the President of India 2006. Elected Fellow, All Indian National Science Academies. Elected Fellow, the World Academy of Sciences, Trieste, Italy. The Fellow, International Union of Pure and Applied Chemistry, IUPAC, and Royal Society of Chemistry, UK. Lifetime Achievement of Contribution to Indian Chemical Industry, Indian Chemistry Council 2009, and several other distinguished awards. And visiting professors, Center for Rapid and Sustainable Product Development, Politecnico Leri, Marihana Grande Leri, Portugal. Distinguished visiting professor, the King Abdullah University, Science and Technology, Saudi Arabia. Harold A. Morton, Distinguished Professor of Polymer Science, the University of Akron. And L. Autocam, Visiting Professor of LCPO, University of Bordeaux, France, 1995. Apart from these recognitions, Professor Sivaram contributed 250 research papers, review articles, and chapters in the books. He is the inventor of 51 patents and 52 Indian patents, all 103 total patents he contributed by his group. Then he guided and supervised 40 PhD students, 20 master's students, 15 postdoctoral fellows. Membership in national committees, member peer review committee, Discipline of Chemistry, IIT Palakkad 2021, member board of advisors, Reimagining Innovation and Science Policy, Mumbai 2021, member Inspire Faculty Fellows in Engineering Science Selection Committee, Indian National Science Academy, New Delhi 2021, advisor External Research Advisory Committee, Indian Institute of Technology, Guwahati 2020 to 2023, Chairman, Research Advisory Committee, CSIR, Central Salt and Marine Chemicals Research Institute, Bhavnagar, 2020-2023. Chairman, Expert Group on Project Mission Coal to Methanol, CSIR, New Delhi, 2020. And project leader, pilot projects on safe laboratory practices and laboratory waste disposal, INAE and DST, New Delhi 2019. Chairman, Committee to recommend technology transfer term on NMITLI projects on fuel cells, CSIR, New Delhi. Chairman, 3-member committee appointed by the DG CSIR to probe the allegations by PUBPR regarding the data manipulation scientific publication 2019. Chairman, Supra Project Advisory Committee, DST, ACRB, New Delhi 2019-21. Chairman, Review Committee of Ramanujam Fellows, DST, ACRB, New Delhi 2019-21. And Chairman, Board of Studies in Polymer Science, Somaiya Vidya Bihar University, Bombay 2018. Chairman, Program Advisory Committee, Domain 8, Manufacturing Technology, Imprint 2, ACRB, DST, and MSRD, Government of India 2018-22. Chairman, the Jury Chemical Sciences and Technology Vasvik Awards 2011 to present. And apart from that, Professor Sivaram is a member of the Scientific Advisory Boards, Biome Therapeutics, Apollo Tires Limited, Asian Paints, TCG Life Sciences Limited, Haldia Petrochemicals, He is a consultant of Reliance Industries, Atul Chemicals, Expanded Polymer System Limited, Mumbai. Member Board of Directors, GMM Hodler Limited, Mumbai. Chairman of the Board, Asian Paints Limited, Mumbai. Apcotex Industries Limited, Mumbai. Deepak Nitride Limited, Vadodara. Supreme Petrochemicals Limited, Mumbai. Ghada Chemicals Private Limited, Mumbai. Beyond Therapeutic Limited, Vadodara. Society for Entrepreneurship, Education and Development, ISR Pune, as a founder director. Mentor, he also mentored the startup companies, Solitaire Initiative Private Limited, Bhubaneswar, Odisha. Found 3D Solutions Limited, Pune. Genrix Membrane Systems Limited, Pune. Orthocrafts Limited, Pune. Venture Center NCL Innovation Park, Pune. And the Research, Innovation and Scientific Entrepreneurship Foundation, ISR, Kolkata. So from the issue, Professor Sivaram, his group is actively working in the research areas for the last 4 years. He has continuously contributing the high impact factor research papers and patents in ISR Pune. So with this brief introduction, I have made it very short and just to escape some of the other achievements. But since the time constraint was there, I had to complete within 5 minutes. So with this note, I request Professor Sivaram to deliver the lecture. So over to Professor Sivaram, please.
Thank you. Thank you, Professor Negi. I hope I am audible. If there is any problem with the audibility, please bring it to the attention of Professor Negi and he can communicate with me. I'd like to thank Professor Negi for his very generous introduction. It's indeed a pleasure to see all of you on the screen. Yes, I agree that it would have been far more pleasanter and purposeful if you can see each other in person. But then this is the reality of the present times. I also like to thank Professor Govt for his kind invitation to deliver this talk today. It was he actually invited me last year and we couldn't make that happen last year because of the pandemic. And therefore now we decided to do this online this year. Thank you, Professor Govt, for your kind courtesy. This is a topic that I have chosen because I felt that for an audience which is fairly diverse and broad spectrum, maybe this topic could be of a general interest. My name is Dr. Sivaram, as you know. I have an email which is mentioned here. The idea of providing this email is if any one of you have any comments, any opinion or anything that you wish to discuss with me, please feel free to contact me on the email after my lecture. Because sometimes in these online deliberations, the interactive processes is not very comfortable. And therefore, if you have any comments or questions or any thoughts that you wish to share with me and seek my opinion, please send me an email. With this little introduction, let me proceed ahead. We are talking about polymers, and polymers are generally called plastics by common man. And, plastics have a very long history in a way. It is, in fact, it is 150 years plus since the first discovery of plastics. And that happened actually in 1868 by a gentleman called John Wesley Hyatt, who actually made a billiard ball, from cellulose nitrate plasticized with camphor. And it's very interesting because prior to this period, the billiard balls were made out of ivory. You can imagine what an expensive material a billiard ball could have been. And it was Hyatt who came up with this discovery that you don't need ivory to make a billiard ball, and you can actually make it from cellulose nitrate plasticized with camphor. So that is actually the beginning of thermoplastics in our world. And in fact, that's about 150 plus years. And just last year, we actually marked the centenary of the discovery of the macromolecular hypothesis. It is a epoch-making discovery, sometimes what we call the paradigm shift that happens in science. And that was actually marked by celebrations around the world. Unfortunately, much of the celebrations were canceled again because of the pandemic. And in fact, that was also something sad because we couldn't really mark this 100th year of macromolecules as much as we could. In fact, the symposium of the American Chemical Society to mark that was planned in 2020 could not happen in 2020. It was cancelled, and actually it happened just 3 weeks ago in April 2021. It was called the Spring ACS meeting. And I had a pleasure of giving a talk in this Spring ACS meeting 2021 to mark the 100th year of the macromolecular hypothesis. Well, this is Hermann Staudinger, the man who really set the ball rolling. And he wrote a paper, and this paper is published on June 12th, 1920. And that's the reason why we celebrated the 2020 as a centenary year. This paper actually gave us the definition of macromolecules. And he also showed us, because as a quintessential organic chemist, he showed us that macromolecules are nothing but large molecules connected by covalent bonds. Because this was a simple hypothesis, but it was not known in 1920. And therefore, the fact that we understood macromolecules as molecules created by formation of carbon-oxygen, carbon-carbon, carbon-nitrogen bonds gave rise to the birth of the so-called the polymer world, the polymer industry, the polymer science, and everything began as a result of this fundamental conceptual development that happened in 1920. Well, it has been a quick and long journey. In fact, it's in less than 100 years. The amount of polymers we consume is today greater than 400 million tons. Just imagine, this is in about 60, 70 years. From zero, we have reached 400 million tons. This industry is a great generator of employment. Today, greater than 1 billion people in this world are in some respect connected with the polymer industry. That's a substantial number, because that's something close to almost 14%, 15% of the world's population is really involved in some respect with polymer industry. The global consumption is approximately 30 kilogram per capita, and it is really a business turnover value of close to 1.2 to 1.3 trillion US dollars per annum. So it's a huge industry today. The structure of the industry we all know. I don't want to spend time on this. It is actually a post-World War industry, World War II industry. In fact, the first of the polymer commercial manufacturing happened around 1945. And therefore, that's what I said, it's just about 70 years that this industry has been in existence. So I think it is a remarkable growth of a new industry. I cannot think of any other new material industry that has grown as fast as polymers industry has grown in the last 75 years. Well, we are going to be talking about sustainability issue in polymers. This is the word sustainable. So what is it with specific reference to polymers? How do I define sustainability? This is a definition that I have defined myself. You will not find this, the way it's written, you will not find it in the literature, but I thought this is a easy way to understand what is sustainable polymers. Now, sustainable polymers are defined as materials derived from renewable or non-renewable resources that are safe in production and consumption, and which after their use can be recycled or disposed of in ways that are environmentally benign. Now, every word here is meaningful. I will not spend too much time on it, but I hope that you will start keeping this definition in your mind as you hear my lecture, as you go forward, and also start thinking about the relevance of this definition, because the word sustainability is used rather loosely, and therefore there is no clarity in the way people use the word sustainability. And therefore, you will see all kinds of scientific papers published which talk about sustainable X or sustainable Y. But I think you have to ask yourself when you read these papers, are they truly meeting the definition of sustainability? Now, what do I mean by recycle? Recycle, it means easy, and this is very important, economically viable process to recycle the material. Disposed of, what do we mean disposed of? It means in land and water, and the products of degradation of a material is harmless to both soil and water. Now, if you kind of bundle all these things together, it's almost impossible to find a material that will really meet all these requirements. And that's where we are facing a big challenge today, because none of the material that we consume today really meets every one of these, specification. Some of them will meet some, but not all, and that's the problem that we are facing today. And that's what I will try to illustrate in the next few minutes. Well, what is the problem? And this is also something which I keep asking, and I want people to ask. Most people think that the use of a fossil hydrocarbon derived building blocks for polymer is a problem, because all the monomers that we use for making polymer predominantly comes from petroleum based hydrocarbons. So many people think that is that the problem of sustainability, or it is after use and end of life issues? What is the real problem? Now, so many people think that it is the use of fossil hydrocarbon is a big problem in the case of sustainability issues associated with polymers and plastics. I want you to think about it a little bit, and I will provide you an answer as we go forward. But I always say that for any problem, if you want to seek a solution, you must actually frame the question very clearly. And because of this ambiguity in these two questions that people have in their mind, people get mixed up. People say, oh, this material is derived from a non-fossil hydrocarbon and therefore it is sustainable. Well, not necessarily so. And I think that's a message that I am trying to drive home at this point of time. Sustainability is a difficult choice. It's not easy. All of us would like to live in a very sustainable environment, sustainable world, but evaluating data and evidence-driven options for making a wise choice based on the principle of what is called the lesser of many evils. Because there is nothing like a solution which is absolutely free of any evil. Okay? So you'll have to look at multiple evidences and then look at what is it that is lesser of the many evils that you are trying to think of. No decision on sustainability is without a consequence. And that is again something that we must understand. But we need to think of the unintended consequences of any decision that we make. And that is very important, because we cannot create a new solution which will result in a new problem, let's say 10, 25 years from now. Okay? Because the problem that we're today facing with, let's say, plastics and polymers as a sustainability question was not created yesterday. It was created 75 years ago, and today we are facing the consequences of that decision. Therefore, any solution that we suggest to the society, we must ensure that that solution does not have an unintended consequence. And that's going to be an extremely important point in defining a solution. And therefore, I always say the real danger in sustainability problem is in simplifying a very complex problem. And that's something that a humorist and a journalist called H.L. Mencken in the US very, very nicely said. He said, for every complex question, there is a simple answer, and that simple answer is invariably wrong. And therefore, don't look for simple answers, because we don't have simple answers. These answers cannot be very simple for such complex problems. Well, So let me address what is the real question, because I asked you, I want you to focus on the real question. So if you look at plastics demand today by application, about 40% of the plastic that we produce, about 400 million tons of plastics we produce, I told you. So 40% of that is close to 160 million tons of plastic goes in what is called packaging application. And that is this big pie here. About 40% goes in packaging application. Now, the rest of it essentially is in building, engineering, and others. The rest, say 60%. Now, what is the problem? The problem is that is a real problem. The packaging application is the real problem. And the entire thing about plastics and packaging is that what do we do with that packaging material after we have finished with that use of that packaging material? And what is the end of life of these packaging materials? Now that is the question. To me, this is the core of the sustainability problem of plastics and polymers. It is not that plastics and polymers are produced from fossil fuel. I don't have a time to discuss that, but I can share that with somebody who's interested, that is actually not a problem at all, honestly speaking, because even today we consume less than 8% of the hydrocarbon that we produce as feedstocks for making polymers. 91 to 92% of the hydrocarbon we burn in our automobiles. Okay, so that 8% hydrocarbon is never an issue in this world. We will have enough of those hydrocarbons for many, many, many centuries to come. So that's not an issue at all. The issue is really this, since a large part of plastics are used in packaging applications, and packaging applications are short life cycle applications. What do we do after we consume the packaging, packaged material? Where do we throw this packaging material? And that is a fundamental problem that we face today. And look at this, and this is again a very, very revealing slide, which also focuses on the problem that we need to solve. If you just look at this pie here, 56% of the packaging market, 60%, and actually if you add PET, it is 80% of the packaging market belongs to two families of polymers. One is a polyester, the other is polyolefins. And therefore, if I look at packaging as a major area of concern, within that packaging, 80% is actually polyolefins and PET. And therefore, I believe that if you're looking for solutions, if you're looking for scientific innovation, you have to look at how to replace these two materials with hopefully more sustainable materials. There's no point in looking at anything else, because everything else is trivial, because you always have to catch the tiger not by the tail, you have to catch the tiger by its head, because there's no point in catching a tiger by its tail. You can never control a tiger. So the other question that you have to see here, other number that you have to see here is look at this per capita consumption of packaging plastics. This is, total plastics is not packaging plastic, total per capita consumption. India is about 20 kilogram per capita. EU is 80, US is 100, Japan is 60, China is 80, almost like European Union. Okay. Now what's the issue? The issue is that if you plot the plastic per capita consumption versus GDP, well, you can always find a relationship between any X and any Y, and this X and Y also seem to be related, and there seems to be a relationship. Higher, the more developed the countries, higher is their per capita consumption of plastics. Okay, the less developed the countries, it is China may be a little bit of an outlier in this, but otherwise most of the less developed countries, their per capita consumption is lower. Now, there is a message here and there is a lesson here. The message is it necessary to increase your per capita consumption of plastics if your GDP is growing? Can we decouple the GDP growth from per capita consumption of plastic? And the second thing is essentially, this per capita is a meaningless number because the actual problem is the value multiplied by the number of people who consume the product. And that, if you look at it that way, India has a tremendous problem. Of course, China has an equally big problem. With 1.3 billion people, just imagine if our per capita consumption was something like Japan or EU, 60 to 80 kilogram per capita, with 1.2 or 1.3 billion people and growing, this would become an insurmountable problem for us. We just cannot manage this problem. Therefore, I think this is a very nice way of illustrating that we have to somehow decouple the economic growth, the GDP growth, with consumption of plastic, because we just cannot do the same way that other people have done in the past, because then we are, then I think hubris is waiting for us. I mean, if that's what we are going to be doing. Well, let me go back and now tell you what more I can tell you. What is the real problem? The real problem is because human race has become consumption driven. Okay. As a civilization, the humanity that we see today is consumption driven. And if you look at this, you can see all these numbers, 8 billion metric tons of plastics we have produced since 1945. And out of this, 60% have been landfilled, and therefore they're existing in some form or other under the soil, because as you know, most synthetic plastics do not biodegrade. They exist for centuries, even if you landfill it. And very, very little of this has really been, recycled and reused and things like that. And if you look at, let's just look at these plastic bags that you and I very commonly use. 1 trillion single-use plastic bags is used every year. And we generate 2 billion tons per annum of municipal waste. 5 million tons of plastics find their way into our oceans. Can you believe that? Because of the way we handle the end of life of these plastics packaging waste. And therefore, unsustainable consumption is the main problem. Okay, so sustainability issue is related to unsustainable consumption by humanity. And that we should not forget, because if we think that there are solutions, if there are science and technology driven solutions, these science and technology driven solutions will not work if we continue to consume materials in a manner in which we are currently consuming. And I think that's something that we need to think about. Well, just look at this one example, something which is very familiar to all of you. Therefore, I am showing it here. We consume actually 500 billion bottles, of water bottles, Pepsi, Coca-Cola. Okay. Water bottles alone, we consume 30 billion liters of bottled water annually today. Okay. And every second we live on this planet Earth, we are throwing away 1,500 bottles. Okay. And we actually produce, these numbers are mind boggling. We produce 20,000 PET bottles every second of our existence in this world. Can you believe this? And the question basically is, what happens to all these bottles? Okay, how much of it is recovered and recycled, and if it is not recovered and recycled, where does it end up ultimately? And that's a question I think we should ask every time you take a bottled water, every time you take a bottled Pepsi or a bottled Coca-Cola in a PET bottle. Think about it a little bit before you consume it and throw the bottle into your dustbin. Okay, because maybe your action, if you're a little bit deliberate in your action, maybe you can save this planet as an individual. Okay, so please think about it. Don't just take a bottle, open the cap and drink it and just throw it in your dustbin. Okay, just think about it. What's going to happen to this bottle after I finish drinking the liquid that is inside this bottle? And if you start thinking about it, if every thinking man and woman in this world starts thinking about it, we can probably solve this problem. Well, what is the solution to this problem? That's a question that we need to ask. Well, this is the reality. What's happening today? You see all these things dumped everywhere. Okay, this is India. All right. I show this is a picture which is a place in Bombay called Devnar. This is actually called the world's largest garbage dumping ground. This is the world's largest garbage dumping ground. Okay. By the way, the height of this mound, which is becoming like a mountain, is already about 30, 40 feet today. Okay, from the ground level. All right. You see this. This is in the road. You will see this. You drive into Bombay, you see this. Okay. Uh, and recently, in the last 2 years ago, there was a huge deluge in Kerala, and this is a picture that somebody sent me of a bridge across a river. After the water had receded, this is what you found on the bridge. And what do you find on that bridge? All these bottles that has gone into the river. Okay, and what you saw is the remnants of that debris that is there in the rivers of India. So these are dire consequences that we are facing. The problem is what now I come to is basically we have to ask ourselves a question every time we use a plastic or a polymer. Where does it end up after I finish using it? Okay. And if all intelligent, right thinking people ask this question and spend a few minutes deliberating on it or seeking information on it, you will make this world a better place. Okay. Now, what we do is we actually use a plastic product. Sometimes we use it just for a few hours. Sometimes we use it for a longer time. Okay. Now, we can reduce the use of these products, and I think that is eminently desirable. I think we should not use plastics where we don't need it. Okay, and that's the first rule of sustainability. So do not use it where you don't need it. If you can avoid it, please avoid it. And that's the first rule of sustainability. The second rule of sustainability is, okay, if I have to use it, if I'm compelled to use it, then you reuse that material as much as you can before you discard it. And that is the second rule of sustainability. Well, but then you can never use any material infinitely. Okay. Sometimes you can't reduce, you need that material. So you will generate waste. And this is inevitable in every society. Now, when you generate a waste, if the waste is properly collected, segregated, subjected to a variety of end-of-life solutions, we would live in a utopian world, nice world, where we have no problem. Okay, but this does not happen. That's the reality. Okay, efforts are being made depending upon the countries in which you live in, but this collection of the waste is the weakest link in the problem that we face today. So what happens is much of the waste that we throw away ends up in what we call the non-collected waste. And that's where the problem comes. So once it ends up in the non-collected waste, it slips into what is called unlegislated losses to environment. It can either go in the land or it can go into the oceans. And that's the problem. And today, this is actually a very, very I call it an underestimate, but this is the best that numbers I could get. 2 to 3% of our annual production of plastics material end up as, in this region of non-collected waste. It's not true across the world. In some parts they do better, in some parts we do worse, but I think this is what the number I have, but I have a difficulty in accepting this number. I think this number has to be much higher than this, but this is something that you get in the literature. Well, and then you ask yourself, how much of the plastics waste is mismanaged? Because I can tell you very little is managed well. And in fact, the management, honestly speaking, looks to be a function of the economic status of the countries. The poorer the country, the poorer the waste is managed. Okay. The high income countries, HI, you can see this is the growth of the mismanaged waste from 2010 to 2025. They're almost in good control of the mismanaged waste. But look at what is called upper middle income countries and lower middle income countries. India comes somewhere in the so-called between upper and lower middle income countries. Look at the mismanaged waste. It was something like 15 million tons in 2010, and it's going to jump to close to 35 million tons by 2025. And this is a real concern because the poorer the country, the waste is mismanaged more. And that's the reality. And that's a problem also with facing India. Well, now, if you go and ask somebody who is dealing with plastics, he says, no problem with plastics. Plastics, what is the problem? We can recycle every plastic, okay? We can reconvert them into useful products. So what's the problem with plastics? The question is not so, the answer is not so simple. Because with every recycle, you are subjecting the polymer to a thermal history, and there's a loss of property. And this loss of property is called downcycling. So recycling, we should call it downcycling, because when you downcycle something, you are actually destroying the value of the material. And that's what we have to recognize. The recycle, will not solve our problem, okay? In fact, recycling only postpones the problem because how many times can you recycle? Maybe 2 times, 3 times. Afterwards, what happens to the material? Material is still there, right? Therefore, you can postpone a problem, but you are not solve the problem, okay? Ultimately, you have to still ask yourself, what is the grave? What is the graveyard for this material? Even after, say, 1 or 2 or 3 recycling, if it's possible. Actually, what we need is processes that do not downcycle. We need processes that upcycle a material. And that's where the concern has been in the recent years in the science literature as well as in industry. And the question is, how do we upcycle a waste material? And I think so we should use this definition properly. Then I think we start asking the right question. And upcycling solutions for plastics is actually in infancy today. We don't have too many options for upcycling, and that's a challenge for both scientists, technologists, and industry. And that's where the problem comes. So we will have to look at this. And second thing is, even assuming that you have an ideal recycling environment, there are many polymers that just cannot be recycled. And this is by nature of the polymer itself, because it's too expensive to recycle, and therefore nobody would recycle them. I give you some examples of those polymers here. I don't want to read this. I think you all are familiar with this. Many multi-phase polymers are difficult to recycle. Many multi-layer co-extruded films that you routinely use. Your potato chips, that you buy every day, the Tetra Pak that you buy for drinking a Maaza or a buttermilk from Amul. All these things are difficult to recycle, okay? And we all use them. And what do? We buy a drink, a soft drink like Maaza or Amul buttermilk. We just drink it. It takes just 5 minutes for us to drink, maybe 10 minutes for us to drink. And then the whole thing goes into a waste paper basket. If you have a waste paper basket, most people throw it on the road because they don't even look for a waste paper bin. So that's where the problem. What do you do with the Tetra Pak? How do you recycle a Tetra Pak? Okay, we still don't have answers. And of course, there are many more of this type which I list here. There are many things that we cannot recycle because either we don't know how to recycle or it's too expensive to recycle. And therefore, the recycling options do not exist. And therefore, what do we do with such materials? And this is also a question that you need to ask yourself. Well, people will tell you, especially if you talk to the industry people, they will tell you that, oh, we have got a robust recycling industry. There are rack pickers who pick up everything from the roadside. They take it to a kabadi wala who takes it to a reprocessor and it goes into some useful products. Well, that's a myth. Don't believe that, because our recycling is not an industry. Our recycling is an apology for an industry. It is actually unorganized, often illegal, poor practices on health, safety, and actually depends on what is called very poor people who have to do this to live their life, you know. And actually, I call this that the Indian recycling industry exploits the divisive fault lines of our society, namely class, caste, and income inequality. In fact, the people who pick up your garbage are the people who are supposed to be picking up your garbage because of the societal norms, which is unfair. You know, why should someone else pick up your garbage? You know, if you are responsible for garbage, you should pick it up yourself. But you can't ask another person because he belongs to, let's say, a disadvantaged strata of society to make you live clean. That's not fair. And I think that's a real problem with recycling. And yeah, and recycling, and if the recycling is so attractive, I asked this question to my friends in industry, why has nobody invested in this industry? Okay. Why has it been left to this unorganized sector, which is actually doing a very, very poor job of recycling? And that's because there is no money in recycling, and therefore no industry is interested in recycling. And therefore just the people who are fringes of a society, people who live on the fringes of a society, who do not have any other income or livelihood, are condemned to do this job. And they are doing this job at great risk to their health and safety, which is, I think, the saddest part of the Indian recycling industry. When I mention this, my friends in industry get very angry with me, but that's the reality and we can't forget this reality. Well, we all have heard about this. So what happens? All the plastics that we throw away here and there enter the waterways, enter the river. And in fact, India is actually has two rivers, which is considered to be the world's largest dumper of plastics in the ocean. Okay. I mean, we have two rivers in India, Brahmaputra, which of course passes somewhat through India, and the Ganges. And these two rivers carry all the plastics waste that we throw away eventually, which ends up in the waterways, and eventually they dump it in the ocean. And that is now creating what is called this huge challenge of microplastics. And I think you're all familiar with this. There are very recent articles on this. I quote here for you, just published a few months ago. This is actually published just a few days ago. Okay. This is 6th May 2021 in Nature. It just published a few days ago. And this is attracting a huge amount of global attention from scientists as well as engineers as well as technologists. And they're all asking this question, is it something that we need to avoid? Is it something that we need to do something about? And in fact, you know, much of these plastics are ending up from our consumption of materials. For example, your own tea bag that you use. What do? You take a tea bag, put it in your dip into your water, and then you just throw it in your dustbin. The tea bag is actually non-woven polypropylene. Okay. So what happened to this non-woven polypropylene? Will it be recycled? No. Where will it end up? Eventually in the oceans of the world. And that's the reality of using a tea bag. Okay. Maybe we should stop using tea bags. Maybe the old-fashioned method of making tea is still good enough for us. Okay. But this is where I said you have to start making choices in your life. The same thing, you have a polyester shirt, and if you use a washing machine, there's some amount of turbulence in a washing machine, and therefore you shred fibers from your garment, and these fibers end up in the oceans. So the question basically is, maybe you should not wash your polyester fabric in a washing machine. Maybe you should wash it with your own hand in a bucket and a water consisting of a detergent. Maybe that's safer. Well, those are the kind of changes in lifestyle that we need to make if you want to solve some of these problems. Well, recently, in fact, this is the paper just published a month ago in Proceedings of the National Academy of Sciences, one of the probably the topmost journal of the world, which says that these microplastics are also part of the particulate in the atmosphere that we are breathing. And this is the first study that shows evidence for this. This is the first time that evidence has been, this is of course in a particular geography in America, but I don't think there are such data available from anywhere in the world, but this is the first of the study of this kind, which says that plastics in microparticle form are found in dust, which we inhale. And therefore, we do not know what the consequences of this particular inhalation of microplastics is for us as citizens. So this is another alarm bells is now ringing. I think a lot of data will have to be collected before we can start thinking about it more constructively. Well, therefore, what people are saying as in the recent years is instead of using this linear process of taking something, making it, using it, disposing it, and ultimately it ends up in landfills, it ends up in the ocean, it ends up maybe in the air. Can we do something by which we can circularize this entire economy? And this is called the circular materials economy. And here what you do is you basically take a monomer, convert that into a polymer, you use it, and then do something. And this recycling is not mechanical recycling. You convert it back to the original monomer. Okay. So we call this chemical recycling. And this is something you will see now enormous amount of literature coming up in the published journals. People are talking about chemical recycling. Chemical recycling is, can I take the polymer and convert it back to the monomer again? Okay, rather than converting the polymer into, let's say, a mechanical recyclate, which is again a polymer. But can I convert it to a monomer, and maybe the monomer can be reused to make a polymer? And this can, in principle, it looks very elegant, but this is the most difficult part, how to convert a polymer to a monomer. As I said, 100 years, we have worried about how to convert a monomer to polymer since Schrodinger's epochal discovery in 1920. And now in 2020, maybe we should start thinking, how do I convert a polymer back to a monomer? Okay. Well, therefore, this is again a very recent paper that you can read in Anguvante Chemie, which says that the chemistry of transformation, which is what chemistry has always been about. If you look at chemical sciences, the entire chemical sciences is nothing but the chemistry of transforming matter. Okay, transforming one form of matter to another form of matter, right? That's what chemistry is all about. Now, what is people are saying is, can you convert that into the chemistry of reuse and therefore a circular process? So a linear process here, can we convert that into a circular process? Now, they all look very elegant. They look simple when I show them in these kinds of graphics. But I can tell you, you take an example of a polymer and ask the questions, can I do this? And you will see what kind of challenges you will face in doing it. Well, I'll skip this slide. And there is a lot of literature now coming on circular chemistry. In fact, it's worth understanding this because this gives us a kind of a clue as to where we may want to go in the future. But I can tell you, these are challenges that we know we still have to meet in terms of completely understanding the nuances of these things. And this is a description of what is called circular chemistry. And I always say the concept of circularity is very elegant. You know, who doesn't like circularity? In fact, nature that we, the nature that we see around us is extremely circular. Okay, just look at every process of nature; it is circular. Okay, and therefore, circularity is very elegant, but it's very difficult in practice. Why it is very difficult in practice? Because any form of transformation of matter requires energy. Okay, anything can be recycled, but the question is how much energy I will need to recycle it. Now, just take an example. When you take propylene or ethylene and make polyethylene, okay, what have you done? You have actually, released a lot of energy because you are formed from one carbon-carbon double bond. You are now formed thousands of carbon-carbon single bond, okay, which are very, very stable in terms of energetics. And therefore, if I have to break that polyethylene and convert that into ethylene, Well, the laws of nature tells me that that much energy that I released will have to be put back. Am I right? Well, that's it. That's as simple as thermodynamics can be. Now, that's not easy because that amount of energy, I have to get that energy from somewhere. Okay. And therefore, it's not so easy to apply energy and break polymer chains, because then I have to have that energy input, right? And where does the energy come from? Okay. And that's a question. Therefore, this is a very fundamental problem in circularity. Everything can be kind of taken back to the monomer, but the question basically is how energy efficient can you make it? And that's not a question that we don't have an answer. And therefore, I always say that when it comes to circularity, learn to distinguish where circularity makes sense and where it does not make sense. Don't just assume that everywhere circularity will make sense. You have to do a good energy balance calculation before you take a call about circularity. And secondly, define the problem correctly. View the evidence dispassionately and implement the solution wisely. Poorly designed circular economy concept would be yet another example of good intentions leading to regrettable consequences. So please be sure about your fundamentals when you plan for circularity. Well, just a few minutes. I'll take another 5 to 10 minutes and I conclude. As I said, if you really want to solve the problem that we are currently facing, you have to focus only on 4 polymers. Okay. Don't worry about the rest of the polymers. Sometimes I find that people are worried about all kinds of polymers, which is not important at all. That they are not short life cycle polymers. These are the 4 polymers which are used in what are called short life cycle application, which is predominantly packaging applications. Okay. Now you have to ensure that you find substitutes which are more sustainable than these 4 polymers. And that's the challenge because we don't have it, unfortunately. And the reason is that all these polymers are highly crystalline, they are non-polar in nature, and they're hydrophobic, essentially. And because of that, they have poor environmental and biodegradability. Okay. Now, the reason is basically because you wanted all these properties. That's why you're using this material. And now you can't say, no, no, after I use, somehow make this property disappear. It's not possible, right? And that's where we are stuck into a kind of a situation where we do not know how to get out of this. Well, in fact, polyethylene does not biodegrade. In fact, there are lots of people who will come and tell you, I've got a solution to biodegrade polyethylene. All of them are based on very poor science. Okay. People add something to polyethylene and say it biodegrades. Okay. It's all in, I mean, I don't want to use the word, but it is just sheer nonsense. Polyethylene cannot biodegrade. Okay. Now, as I said, it's because of the very high molecular weight and crystalline structure. Okay. But if you can convert that into low molecular weight alkanes or alkenes, which is about 50 to 80 carbon atoms, then they can undergo biodegradation and bioassimilation because they are now, the bugs can assimilate them, bioassimilate them. Okay, but you have to get to a carbon number of about 50, you know. So whereas classically polyethylene has a carbon number of close to 5,000. Okay, so you just cannot do this. Polyolefins, of course, can undergo because they are hydrocarbons, right? They are carbon and hydrogen. So in no way they are different from your gasoline. Except your gasoline is a liquid, this is a solid. So this is a solid fuel, essentially. So if you have an oxygen and you can incinerate them, well, it will burn into form carbon dioxide. And this is not something you want to do because if you want to incinerate a plastic, you are increasing the carbon dioxide load in the environment, which is something today people will say that's not, no, that's not acceptable, right? I will not do anything that will enhance or increase the load of carbon dioxide in the environment. Well, you can pyrolyze them in what is called oxygen-starved environment, where there is no oxygen, to short-chain hydrocarbons in the gasoline and diesel range. And this is what is called plastics to fuel technology. But this is where I said that thermodynamics does not help me. Okay, the amount of energy that I have to spend in generating this hydrocarbon is about the same as what the energy content of the resulting hydrocarbon is. So the net energy gain is close to zero. Okay, I have to supply heat energy to polyolefin to break it down, and then I get a fuel, and the calorific value of the fuel is equal to the calorific value that I expended in making the fuel, and therefore the net energy gain becomes close to zero. And that's one of the reasons why this process is, although everybody says I can make fuel out of waste plastics, but it is not economically viable. And this is because of the energetics. Okay. And that's why I keep on asking people, anything can be broken down into anything, but is it makes sense energetically? And I think as students of chemistry and chemical engineering, please apply the laws of thermodynamics to every problem that you are faced with. And you will probably get a better answer than many other people who claim some kind of a solution. Well, a lot of work has been recently described in upcycling polyolefins. Now, whether these are going to be relevant, whether these are going to be economically viable is an open question, but a lot of research is going on, okay? At this point of time, many of them are proof of concepts. You can see here, they're all very recent papers. This is 2020, this is 2020 Science, this is 2020 Nature Catalysis, this is 2017. And here you can take polyethylene and convert them in a variety of reactors, in a fixed bed reactors, in a fluidized bed reactor, in a microwave reactor, to a variety of products. Some of them are very valuable products, okay, very valuable products. And now we call these things an upcycling technology, because the products that you derive here have a higher value in terms of, let's say, per kilogram value than polyethylene itself, okay? Now, of course, you have to factor in the cost of transformation. Now, that's not something that people have yet looked at, but the products have good value. Okay. Now we have to look at whether the cost of transformation is manageable in terms of both energy and mass balance. Now, this is something that people will start looking, but I think these are options that are being thrown out at this point of time. Lots of emerging chemistry for sustainability is coming. I will not have too much time to discuss all these things. There is, if you open a journal today, you will see so many papers being written on this. I just give you the headlines here, the titles that you will see. Closed loop recycling of polymer that mimic the properties of polyethylene but have hydraulically degradable linkages. Use of designer enzymes for chemical recycling of polyesters. Use of dynamic covalent bonds for closed loop recycling. Designing monomers and polymers with infinite chemical recyclability. Self-immolative polymers. Polymers designed for what is called apoptosis. Apoptosis is something that we know happens in cells. Cells die after their function is finished. Okay, all over in our human body we have cells, and these cells die when the function of a cell is completed. Can we design polymers that will die after its use is completed? Okay, and we call it self-immolative polymers. And of course, vitrimers is a new emerging class of materials which is looking at whether we can recycle thermosets. I have not talked about thermosets today, but thermosets are another important class of polymers. And can we recycle thermosets, which conventionally we have been taught in our undergraduate degree course that thermosets cannot be reprocessed. Okay, the question is, just like thermoplastics, can thermosets be reprocessed? So that's a question that now looks like it's possible to do so with the right chemistry, and that chemistry is called the chemistry of vitrimers. And I can't spend time on all these things. They are very fascinating subjects, many, very interesting chemistry that is coming. But I think whether some of these will offer practical solutions to the problem we face today, only time will tell. Okay, it's too early to tell at this point of time whether any one of them have the promise to solve any particular problem that you face today. Well, I talk about all these things: chemically degradable polymers involving cleavable bonds, what is called clean depolymerization with polymers having low sealing temperatures. We use a thermodynamic concept here. Microbial enzymatic degradation of polymers, and of course, polymers with unsaturation like rubbers. Can we degrade them too in some manner? And these are the kind of questions that people are now asking. And this is just one example. Can you imagine if you have a polyethylene? This is polyethylene. You make a product out of this. You can only do mechanical recycling, right? Okay. Now here is a polymer, which is not polyethylene, but actually it's a polyester, but whose structure resembles a polyethylene. Okay. And this is a very clever way of making the structure. And if you have this polyester, in principle, this can be chemically recycled. And that's the thing that this group of people looked at. This paper appeared in Nature in February 2021. They made this long chain polyesters consisting of C16 carbon atoms. They could be either polycarbonate or polyesters. Interestingly, they show similar what is called fringe vessel morphology as polyethylene. In fact, that's that very interesting part of it. And in fact, you can see here they have compared the properties of these polymers with high density polyethylene, and they are very, very, very close to high density polyethylene properties. But the most interesting part of it is after you use, you can actually hydrolyze them back to the monomers, okay, very easily. And that's the chemistry that they have established here. Now, I still feel that this chemistry is esoteric at this point of time, but I think it tells us that there are solutions that we must be looking for. Okay. Well, this is, you can do it enzyme. For example, can I throw a polymer with an enzyme and typically a polyester into a reactor and I depolymerize the polymer. Okay. Now, this work actually has been going on from 2016, but it has really reached a kind of a very high momentum in 2020. And now there's a company called Carbios in France, along with Novozymes. They're trying to build a semi-commercial manufacturing plant for this. And they are going to demonstrate this for PET, the bottles that I talk about, the bottles that you drink water and throw it away. Can I depolymerize this using an enzymatic process? And they feel that there is economics which is favorable here, but this is yet to be proven on a commercial scale. Well, there are other chemistry I don't have time to talk about. This is what is called the closed loop recycled chemistry, which is using a dynamic covalent bond. And these are polyesters, which cleanly depolymerize to the monomer. Okay. Now, these are very nice polyesters. Okay. And these polyesters are made out of lactones, which are something like many lactones, which we polymerize. And these can actually polymerize and actually very cleanly depolymerize. Okay. And this cycle of polymerization, this is polymerization and this is depolymerization, is so clean that this can be done infinitely. So people call it infinitely recyclable materials. Now, whether these properties of this material will be good enough to what kind of application, we still do not know, but this is something that people are looking at. And lastly, I talked about this. This is what is called the self-immolative polymers, polymers that kind of destroy themselves after some time. Okay, it is like a timeline. It's like a trigger that you create, and after some time, the polymer disappears. And this is actually an area of great interest for defense. For stealth, because there are lots of things they want to make out of polymers. That once the polymer, the object has performed its function, they want the object to destroy itself completely, so that the enemy does not know what this product was. And therefore, defense is, especially advanced countries, defense departments are investing a lot of money into this kind of research, and eventually maybe some benefit will come back to, let's say, everyday products. Well, chemical recycling is therefore a great area of interest today. If those of you are interested, please read this review in Anguvante Chemie in 11th March 2020. It kind of gives you an overview of the opportunities and challenges in what is called beyond mechanical recycling, giving new life to plastics waste. And it just opens up a lot of problems and lots of challenges for people to start thinking about in case you are starting to begin your early research in a laboratory. One of the big problems that we must always recognize, and this is something that engineers are very keenly looking at, anytime you supply heat to a polymer, it's not great because polymers are extremely poor conductors of heat. Okay. So I have to improve the thermal conductivity of the polymer in order to subject it to efficient thermal processes. And that's a challenge, because if you want to do thermal processes for chemical recycling, one of the reasons why the energy costs are so high is because I have to subject it to much higher energy content than in order to heat that material, because polymers are extremely poor conductors of heat. Okay, we know that. Therefore, question is, how do I improve the thermal conductivity of a polymer? Okay, can we do it post at the waste stage? Can I add something to the waste by which the polymer becomes much more thermally conductive so that I can subject it to more efficient heating processes? Or can I use other forms of heating, okay, which do not depend upon thermal conductivity? And therefore, there's been a lot of interest today in microwave heating, plasma reactors, supercritical fluid reactors for polymer chemical recycling. Now, this is an area of great interest today, and this is one of the reasons why, it's not just chemistry, but a lot of chemical engineering and principles will have to be used here. And because heat transfer in a conventional chemical reactor is a major constraint, for any thermal reprocessing of polymer in terms of chemical recycling. So please, in those of you who are interested in chemical engineering, must start looking at these problems. Well, that's what I said. We call it molecular recycling technologies. For over 100 years, we have learned how to stitch monomers together to make polymers. And now we must begin to learn how to remove the stitches. We have learned how to stitch them. Okay. Now we must learn how to remove the stitches. We must understand how to convert polymers into monomers. And that's, I think, one of the biggest challenges we face, maybe for the next 50 years. All right. Well, there are lots. I think I have spent my time. I'm going to skip some of these slides. By the way, I can send these slides to you in case some of you are interested. A lot of things that we can do in order to improve the sustainability of polymer. But one thing I want to finish before I say is this, just one comment, because there's a lot of talk today saying biodegradable polymers is somehow a solution to sustainability issue of polymers. And I want to say here, I want to state here that it is not a solution to the problem. Okay. On the contrary, it's going to complicate the problem. And I'll explain to you why. Okay. The reason is that there are lots of materials which are so-called biodegradable, but there are only a few materials which are truly biodegradable, and they are here. Okay. The rest of it are all bio-based polymers. Petroleum-based, bio-based, petroleum-based, non-biodegradable, bio-based, non-biodegradable, petroleum-based, biodegradable, and here is bio-based, biodegradable. Actually speaking, there are only two classes of polymers. One is the polyester, other is the starch-based materials. Unfortunately, most of them are not significant in terms of their properties. Most people are worried about deriving polymers from bio-renewable resources. That is, I said, is not a problem. I think the fact that polymers are derived from fossil fuel is not the big problem. The problem is the waste, how to handle the waste. And if you want to handle the waste, I must have truly biodegradable polymers. And that is something that we lack today. So often biodegradable polymers are touted as panacea of all the ills of plastic. This is a myth. There are only two classes of biodegradable polymers available today. Polyesters, which are derived from sugar, and starch, which is derived from potato. I would rather be very wary of us depending upon material resources for our growth based on sugar and potato. Okay, it's not something sustainable. Okay, I mean, it's okay for small volume application, but look, imagine if I had to make 200 million tons of a plastic. Can I depend on potatoes and sugar for making 200 million tons of plastics? It's just not possible. There are other solutions people talk about. I will not comment on them, but less said the better. None of them are solutions. Okay, all these things are not solutions. They don't have any solutions, but they are all being touted in the market as solutions. In fact, biodegradable polymers, people think as if we throw them away on the roadside, it will degrade. There is no such polymer that you throw away on the roadside, it will degrade. Okay. Even a biodegradable polymer requires industrial composting environment. It requires controlled conditions of moisture, temperature, and you have to have an inoculum. Without the three, nothing degrades. Okay. So very nice to have such, labels, eco-friendly packaging, but this actually, the so-called eco-friendly packaging, you can't throw it in your backyard, it will not disappear. It's not like a banana peel, which you can throw in your backyard, it will disappear. Okay. But this has to be composted and it will take 12 weeks to compost. Okay. In a composting pit. The question is, we still do not have a material which has which has a compostability equivalent to a paper or a banana skin. Okay, we all eat a banana, and what do? We can throw the skin on the roadside, on the near on your curbside, and next day, 2 days later, the banana skin would have disappeared. Unfortunately, we don't have a plastic which will mimic the banana skin. Okay, so therefore, to tell that biodegradable materials is actually a double-edged sword. It can cause consumers to litter more, and it's not going to solve the problem. Okay, and it doesn't disappear, unless you subject it to a very controlled environment, and that's something that nobody talks to you when you talk about a biodegradable polymer. In fact, this is a very highly misused term, and please go and read this paper if you're interested. In fact, there is nothing called a biodegradable material. You can say a biodegradable material in the context of a receiving environment. I call it the receiving environment, which is a grave. Okay, if you define to me the grave, I will tell you whether something is biodegradable or not. But without defining the end resting site of that material, you can't talk about a biodegradable polymer. And most scientists also are saying biodegradable polymers in the literature without understanding this very simple principle. It's very sad that scientific community also is using this term very, very inaccurately. And I think we are not doing service to society. And please go and read this article. This is a nice article which tells do's and do nots when assessing the biodegradation of plastics. I wish people read this and then use the term biodegradation when they claim something to be biodegradable. Well, I will skip this slide. There are lots of science and technology gap even in biodegradable polymers. We have a few, but even there, we have very poor properties in many of them. And I just show here, and that's one of the reasons why they are not becoming very popular. You don't see them on your supermarkets. You don't see them on the shelves where you buy things. The reason is because as a packaging material, they are not very good. That's a problem. And one of the biggest problem they have as a packaging material is this, their water vapor transmission rate and oxygen transmission rate are very, very inferior compared to, let's say, polyethylene or polypropylene. And this is very important for packaging application. Well, there are lots of issues, and on sustainability, I'm going to end this lecture. I think what we need to ask whenever we talk about the challenge posed by nature and environment, we need what is called a normative response. And this is something that social scientists use this word called the normative response. And what is a normative response? Normativity is a phenomenon in human society of designating some actions or outcome as good or desirable or permissible, and others as bad or undesirable or impermissible. A norm in this normative sense means a standard of evaluating and making judgments about behavior or outcomes. And I think we must understand the principle of normative response when we talk about sustainability of plastics. And I think this is beautifully said by a very Native American proverb, says, we do not inherit the earth from our ancestors, we borrow it of our children. And therefore, our normative response is what will tell us whether we are focused on the future of this planet Earth or not. We have to dematerialize. We have to generate more economic value from less natural resources. We have to engage with society. We have to improve public communication. In fact, scientists must not use scientifically unacceptable terms in their conversation. And I find that not only in India, all over the world, scientists are using unacceptable terminologies in defining material attributes, and this is wrong in my opinion. Innovation aimed at sustainability, embed sustainability as a business strategy, and lastly, teach the principles of sustainability to students when they are studying nowadays. I think this is very important. I just taught a full semester course on sustainability and chemistry at ISER Calcutta in the last semester. I am offering this course again starting from August in 2021. 45 students took this course, and I think I got excellent feedback from them. And I think it's important, not only in plastics and polymers. I think we have to look at sustainability in every facet of our human life. And I think that's what helps us to, I think students, I think we, must learn at a very early stage so that they understand this as they grow up in their professional life. Well, ultimately, I think we need to focus on consumption, because I always said that we have to have sustainable consumption, as well as we have to have end of use disposal of short life cycle materials. But without sustainable consumption, no solution of end of use life disposal of a material will give us any kind of what is called a solution to this problem. And also we need to shift the conversation from a binary, which I call the devil versus an angel. Because some people call the plastics the devil, some people call a plastics an angel, and they keep arguing endlessly between them whether it's a devil or an angel. In my opinion, plastics are neither a devil nor an angel. What are they? And that's what the conversation should be about. And I think that only then we can make progress in this area. And I always say that people used to talk about 3 R's. As a scientist, I said, I want to talk about 4 R's. Reduce. I think that's the first. We must reduce whatever we are using. Reuse whatever is possible to reuse. Recycle, but figure out the right way to recycle. Okay. And it should be a scientifically, defined method of recycling. And largely, we have to reinvent new materials. And that's what I talked about. There are lots of new chemistry, lots of new materials are being talked about today. Maybe these will become some of the future materials. So we have to reinvent. And lastly, sustainability. Please don't think that this is a problem of the government. Don't think sustainability is a problem of the industry. Sustainability thinking begins with me, you, and every one of you who is listening to this talk. It begins in our homes. It begins by teaching our children. It begins in our workplace. It begins in the area that surrounds us. If we can take care of it in terms of sustainability, I think you will take care of the world. So don't think that all the problems of sustainability has to be solved by the government, solved by the municipal corporation, solved by industry. No, they will all have to play their part. But if you don't play your part as a citizen, as an informed and concerned citizen, this problem will not go away. So thank you for your kind attention. I just want to say this, that in the end, the power that plastic wields comes from all of us. That's what I said. All of us benefit from it, even as we suffer from its ill effects. Plastic shows our own collective failure as a society, industry, and government. I put the word society first because society is what is most important. Well, George Bernard Shaw said, we are made wise not by the recollection of our past. Plastics had a glorious past, 100 years of glorious polymer science. But I think we have to ask ourselves, what is our responsibility to the future? And kind of recalibrate the science, technology, manufacturing, application to ensure that we are responsible for the future. And lastly, Sir Francis Bacon once said, when you wish to achieve results that have not been achieved before, it is an unwise fancy to think that they can be achieved by using methods that have been used before. And that's why you require discovery, you require invention, you require innovation. Because existing methods are not going to solve your problem. Okay, you require completely new methods. Think differently. And that's what I think St. Francis Bacon said in another context, that you have to bring new methods to solve the problems. And that's the message I want to leave with. This is something that many of you may have seen in your WhatsApp circulating group, but I thought this is something was beautiful, and therefore I have put it here. This is, a picture of a drop of water on a leaf, and 12 ants are drinking that water. Okay, 12 ants are drinking that water. And what have they done? They have divided themselves into 4 groups, 4 into 3, and they have distributed themselves equally on the leaf in order to balance the leaf so that the water will not slide off the leaf. Can you imagine that? Otherwise, if they all went in one direction to drink their water, the water will simply slide off because of the weight of the ants, the leaf will tilt. So what they have done, they have organized themselves in a beautiful manner. And in that organization, they're all getting their supply of water. At the same time, the water is conserved. Okay, the water is not falling off the leaf. What is it teaching us? Cooperative behavior, resource sharing, self-enforced order, frugality. Amazing. And this is what a tiny ant is teaching us. I think we have to learn this lesson from the tiny ant. If we can practice this discipline in our lives, we can create a sustainable planet. And that's the message I want you to be remembering at the end of this talk, that everything is what we have to do as a society that will make a difference. So thank you so much for your kind attention. I think I have taken longer time than necessary. I hope that you will pardon me for this extra time that I've taken. And if there are any questions, I'll be free to answer. Otherwise, please send your questions to me by email, and I will be delighted to respond to you. Thank you so much for your kind attention.
Thank you, sir. And now the lecture is open for the discussion. I request audience, if you have any queries, you can directly ask to Professor Sivaram, or if you want to communicate through email, that is also possible. He has already mentioned about that. So any questions or queries, the session is open now.
May I come in, sir?
Yeah, please do.
Sure.
Sir, it was really very enlightening and very much informative talk. We have many of us are working on this biodegradability, recyclability, and all many things, but challenges are huge. And in fact, after listening to your talk, it seems the solution is not there at all. So, means other
Don't
than
get
I
dispirited,
think,
but the solutions are there, but they're not so simple. That's all,
yeah, only solution is to reduce and reuse kind of thing. Reduce the use of plastics. I feel that is the only solution.
Okay.
Yeah,
No,
there are several challenges which you have already discussed. Really, it is difficult to recycle. So, and if it is burned also, it will cause lot of people have
that's
no
correct.
way
That's
but to
correct.
dump and landfill.
That's correct. You are right. No, that's why I said I wanted to open up. I would be foolish if I say that there is a solution that will solve this problem, because in which case, why the whole world talking about it, right? If the solution exists, okay. The only thing I want all of us to understand is that let's not simplify the problem and tell the society that we have solution, okay? Because the society will not forgive you if you mislead them, okay? All right. So as scientists, as intellectuals, as people who understand science, technology, and its application, we have to be fair in communication, Okay, because I think too many of us or too many people, not only in India, around the world, they come up and the right titles of papers that look as if the problem is disappearing tomorrow. Okay, maybe if you find a way to get your paper published, I have no problem, but that's okay. But make sure that when you are talking to the communities, when ultimately public communication is going to be very important. Tell them what they can do. Okay, tell them what they should do, rather than tell them that you have a solution that will solve the problem. Okay. And I think that is more
Sure.
important. Of course, some of you
Yes.
can have a solution that can solve the problem. That's why I said, we need completely new thinking. Okay. In order to, in order to find solution. It's not that yesterday's thinking will work tomorrow. Okay. So we need new thinking. I'm sure solutions will come, but it's going to take time. It's going to take time.
Okay. Thank you, sir.
Sir, I am OBG. So it's a very interesting talk, and it's a really interactive, and you have given a lot of good example for preparation of different chemicals from your during degradation of polymer. So I want to, because you are a big person in Indian government, I want to share one thing, sir. So why Indian government is not imposing a certain amount of money when we are buying a water bottle? Suppose if we going to deposit 1 rupees when I am going to buy a water bottle, and then if I return to a certain center, the government will uh, return back that 1 rupees money. So that way, people will have a driving force to collect a certain polymer waste and to given to a certain center. So at least government can collect that different polymer, used polymer, your material, particularly for packaging,
I
water
agree.
bottle.
Yeah, correct. I agree with you. I think this is a solution which has been tested and tried in other parts of the world.
Yeah, I have seen in Canada. I have seen in Canada. So they
Works
are
in which
doing
parts
this
of the world?
good, very
Okay.
nice, organized.
Yeah, it works very well. I tell you, you are absolutely right. This is what I said that all of us have to make this views known, and you are right. And all of us have been talking about it. In fact, basically, what they have is a system by which you pay an extra, and when you return the bottle, you get that discount in the next bottle you buy. Okay.
Yes, sir. Yes, sir.
So,
So that way, even small
yeah,
polymer packet, if it
correct.
is 10 paisa, 10
So,
paisa or 5 paisa,
right.
I think
Now, the
that way we
problem,
can.
yeah, the problem is this requires what is called a supply chain logistics, which is called the reverse supply chain you have to create. You have what is called a forward supply chain. The forward supply chain is from the bottle manufacturer to the water company, which is making the water and filling the bottle. And from there, it comes to some supermarket or some kirana store, right? From there, you buy that bottle. Now, this reverse process also has to be established. The reverse process is that you give it back to the kirana or the supermarket, and the supermarket gives it back to that Bisleri or Kinley, and the Kinley gives it back to the fellow who made the bottle for it. Understand? Now,
Yes, sir.
this is not difficult. This is not difficult to do, and I think I have been advocating that industry must come forward to establish this what is called reverse supply chain. Okay,
Yes, sir.
because they are masters in forward supply chain, because they are able to reach the water bottle even in the even in 20,000 feet in the Himalayas. Okay, all right, or in Arunachal Pradesh, you can still get
Yes, yes.
a Bisleri bottle. But the question basically is how does it get back, into the manufacturing company again. Now, this is something they have to organize, and this is where they have to, this cost that we're talking about, they have to levy a cost for this reverse supply chain also. Okay. The forward
Yes, sir.
supply chain you already paid when you bought it. For reverse supply chain also, they have to increase that cost. Now,
Yes,
unfortunately,
yes.
this is doable. This is eminently doable, and this is what I said. The first thing, reduce, and this is called reuse. Because here the same bottle should go back to the bottle manufacturer. Okay.
Yes, sir. Yes. So
And
as I believe, if I able to buy at 20 rupees, so I am also able to, I think, give 22 rupees.
correct,
So
correct, correct.
yeah,
I understand that this is very well done. In fact, this is one of the standard thing in society. For every behavioral change, you have to
yes,
incentivize the society. Okay, all right. You have to
thank you, sir.
provide incentives to society in order for them to change their behavior. Okay, and in India, we have to change the behavior of a large number of people. Okay, because they don't understand the problems, and therefore they are not doing the right thing, and therefore hopefully the more knowledgeable people will do better, will handle it better. For example, I'll give you an example. Are you from IIT Roorkee?
Yes, sir. Yes, sir. I am
I
faculty in
have
the Polymer.
I said Pune, I have set up a system with the help of the student volunteers that all the water bottles that is consumed in the campus is collected, is not only collected, it is cleaned, it is separated, it is cut into three parts: the label, the bottle, and the cap, and it is sent to 3 recyclers independently in Pune. Okay, and I get a premium price for this. Okay, and I have
Thank
made
you.
the
Thank
students do this. Okay, I said, so students are, we have a sustainable, we have a green club of the students, and I worked with them about 2 years ago to set up this process. And now that man from this recycling industry comes directly into ICER, collects these bottles and goes away. Okay, all right. Now, if you in IIT Roorkee, you can do this, okay, within your own campus, okay, or within your own
Yes,
township.
yes,
Okay?
sure, sir. Thank you, sir.
Because these are small things that we can do. Because see, because the reason is the fellow who recycles the cap is a high density polyethylene recycler. The fellow who recycles PET is a PET recycler. And then there's a label, and the label has to go somewhere else. Now, if you throw the bottle along with the cap and the label, then it goes into the garbage eventually. Okay. But you separate them. So we have given them in the cafeteria, in the mess, we have kept bins. And what they do after drinking that water, they put the cap in one bin, they put the empty bottle in another bin, they remove the label and put the label in a third bin. Okay. And students are smart, right? They can be taught to do this. They are all educated people. And it works beautifully. Okay. So I think all of us have to do these small things, and then you will create value for the society. Okay. So, I mean, we can't solve the world's problem by this, but I think if we can implement these things in our own environment, we can solve some problems, which is also important. So, yeah.
Namaste,
So
sir.
please do that in your IIT Roorkee. Get the student volunteers to come and help you to do this. And you will see, you will make money out of this. I'm actually, the student club is making money out of this. Okay.
Sir, namaste, sir.
Thank you.
Sir,
Next
namaste,
one.
sir.
Yeah.
Thank you.
Sir, I am Deputy Registrar from the IIT Roorkee itself. And thank you very much for delivering a informative and enlightening talk, and we are benefited out of it. Sir, there is one submission rather. It should be sensitized at the school level. See, if this is sensitized at the school level, the children level, they are more prone to accept things rather than at a middle age. If they are sensitized about the reuse of plastic and how to not to use the polythene, how not to use the water bottles. If it is a part of the curriculum, certainly over a period of time, that great changes may be there, sir. Thank you, sir.
I agree with you. It is always nice to begin early. But I always say that anybody can begin anytime. I mean, like, we don't have to wait, in fact, for the schools to do this. Anybody who is interested can do this. People can do it in their apartment buildings. People can do it in their colonies. People can do it in their, I mean, within the house, okay. You can teach your children. Okay. So I think it is a collective action. Okay. All I'm saying is, let's not simply say somebody else should do it, because then I think I'm absolving myself from the responsibility. Everybody else should do it, but let me also do it first. Okay. That's my submission.
Um, Sir, good evening. This is Dr. Gaurav Manik from IIT Roorkee.
Yeah.
Let me first congratulate you for the fact that we see several researchers, several academicians presenting their presentations, and fancy presentations and research, and never concluding that we need to have a self-imposed order. I feel greatly indebted to you for moving your presentation in that direction. Uh, However, I have small questions. Uh, First point is that you mentioned that there are several examples of biodegradable sources like the polylactic acid and several things coming from potato and corn. However, you also mentioned that these things, this kind of thing is no, the biodegradability that we are fancying about is not the ideal direction. It's not leading us to where it should be. But however, we have been spending a lot of funding in research and a lot of focus in India as well. So why are we doing this? When you mentioned these biodegradable polymers actually are not truly biodegradable. Rather than you also talked about the focus should be more on depolymerization. So
That's right.
why is the focus has been more on this biodegradable aspects rather than on depolymerization? So are we skewed in our planning, or you have something to advise on?
No, I think you are Manik, right? You are. Am I speaking to Manik?
Yes, sir.
Okay. Dr. Manik, you are absolutely right. Our research is completely misplaced. Okay. And that's what I said. If you want to solve a problem, ask the right question first. Okay.
Right.
Very often, we don't ask the question and we are trying to solve the problem. Okay. And so
Right.
this is also, I hope your students will understand that if you really want to solve any problem, frame your questions correctly. And if you now, the problem is, in fact, by the way, as we speak, just 1 month ago, Australia as a nation has banned the use of biodegradable polymer in their country. Can you believe that now?
It's interesting to hear. It's quite
Okay.
interesting to hear. Yeah.
Now, the reason is because, A, there are multiple issues. See, it can have specialty applications. I'm not bothered about that. Okay. It has biomedical applications. It has some other applications in small volume applications. I have no issues. But I said focus on what is it? I said 100 and 200 million tons of polyethylene and polyesters, right? PET. That's where I have to attack the problem. Am I right?
Yeah.
I'm not attacking the problem of a polymer which is consumed in 5,000 tons per annum, which is true. I mean, some of the biodegradable polymers can go in that application because there is some value there. But we are talking about polyolefins and PET as a area of replacement, okay, sustainability, and that's where the problem comes. Number one, I said 40% of the packaging plastics is essentially coming from these two classes of material, which actually adds up to close to 170, 180 million tons per annum of consumption. Now, if you have a good student, ask him to calculate how much potatoes or how much sugar you will need, to make 180 million tons of plastics. Okay. And
Very
then
true.
you come to the conclusion that this is just not sustainable. Number one. Number two is sugar. The price of sugar, is what is the price of sugar today? It's close to 25 rupees a kilogram. Okay. All right. And how can you start with the raw material, which is 25 rupees a kilogram or 30 rupees a kilogram? That's what the price of sugar you buy, right? When you go to the bazaar and buy sugar and convert that into a polymer, at what price you will convert. Okay. So I think this, and same thing is potato. And by the way, countries like India depend upon starch and carbohydrate for its human energy. Okay. I mean, we are not, people, most people don't eat meat here, and so all the energy comes from carbohydrates, right? Whether it's rice or whether it is sugar or whether it is starch, wheat, it's all carbohydrate. The question basically is that how can I use these carbohydrates, which is needed for human survival, and convert them into a plastic and you throw it away? I mean, it doesn't make sense. You can't make a plastic out of it and make a packaging out of it and then you use it and throw it away. I mean, that could have fed so many people, you know, in terms of the food. I mean, this is ridiculous. Therefore, number one, unless somebody comes up with a clear technology or science that you can make this from other non-edible resources, that's what I mentioned it, you know, then maybe there is some, we need to relook at these technologies as a what is called the substitution for the big volume materials. But as long as they are dependent upon sugar or starch, okay, or even corn basically they convert the corn into sugar, okay. So sugar or starch, I think it's not unsustainable. And therefore, you are right, people keep on doing this kind of a thing and they feel, and I keep telling them that nothing is going to come out of it. You may publish a few more papers, you know, that's all, you know, but it's not going to solve any problem. You know. And I think you hit the nail rightly. There's too much of such research goes on, especially in our country. If it is meant for any very specific end use, let's say in some application, then I don't mind. But if it is generally being said that it's a biodegradable material, it's of no use. Because as I said, in fact, this word biodegradable should not be used without defining the grave of the polymer. Okay.
Yeah, true.
If you can say that this polymer will end up in an industrial composting environment, then I will talk about biodegradability. Okay. But most polymers are not ending up in industrial composting. They're all ending up in the landfill. Okay. In the landfill, on the contrary, people don't realize, why Australia banned it. You see, if you take a biodegradable polymer and put it in the landfill, you're going to generate methane. Okay, and methane is 5 times more, greenhouse gas emission gas than carbon dioxide. Okay.
True.
And therefore, you can't solve one problem by creating another problem, So, if you compost it, fine, but you can't fill it, because if you fill it, many biodegradable polymer will undergo anaerobic digestion, okay, and form methane, over a period of time, and then we get methane in the air, which is also not acceptable, because every kilogram of methane is like, every kilogram of methane is like almost 5 to 7 kilograms of carbon dioxide, in terms of the HT potential. So these are all solutions. So, okay, if you can have a assured composting environment, then it's fine, But,
so, sir, don't you feel we have somewhere lagged in understanding
one more point I want to make is, when you are generating 180 million tons of waste made of PET and PP, if you put let's say 5 million tons in that of biodegradable polymers, do you think somebody is going to segregate it for composting it?
Yeah. No, not possible. Yeah.
Possible, So what is the use, of doing this? That's why Australia has banned it. They feel that they have done a very detailed study. If somebody wants, I will send you the report. And their study shows that on the net, this is not a solution at all, Okay.
Yeah.
I mean, there are other areas of biodegradability. For example, if you're using it for implant, if you're using it for body, for some prosthesis, they're always okay, I mean, that's okay, but that's not the application I'm talking about.
Right. So don't you think, sir, we have somewhere lagged in understanding the complete cycle of the biodegradable polymers, and we just went into that direction without knowing.
That's why I'm telling the scientists, I'm telling the faculty members to please think about these things before you define a problem, and the solution, so those, they are not solution for this problem. Maybe there's a solution for some other problem that you may have defined. I have no issues on that. But it is definitely not a solution for what is called the sustainability issue with plastic that we are facing today, which is basically the waste plastics in the environment.
Thanks a lot, sir. Thanks a lot for your interesting talk. Thank you.
So I think already Professor Sivaram, just talked about more than 30 minutes. Any other queries? You can just pass on our email.
Yeah, I have already showed my email at the beginning of my talk, so you can, I'm sure many people must have noted it. Otherwise, you can always put the, and I don't know, if there's a chat box, you can put my email there.
Can I ask, sir, one question?
Yeah, please do.
Yeah. So, good evening, sir. So, I'm research scholar in the Department of Mechanical and Industrial Engineering, IIT Roorkee. So, I'm also working in the field of polymer composites. Actually, I'm working in the field of natural fiber reinforced polymer composites. And my we being a mechanical engineer, we are mostly focusing on the product development aspect. And today, the lecture that I heard from you about the biodegradability accept, yeah, we have heard about biodegradability, but surely it has enlightened me, and so hopefully not now, but somewhere down the line, I would like to work in this field as well.
Sure.
So I want to I would like to hear from you, sir, that we have heard that Vistara Airlines, they are using PLA based cutleries, and they are claiming that these are biodegradable. So I would like to hear from you, are they actually biodegradable, or what they do after it is being used?
No, that is the whole thing. See, PLA is biodegradable if you compost it at 60 degrees centigrade at 55% relative humidity in the presence of a microorganism as a culture. Okay, you have to add a microorganism which is an esterase. Okay, which is an
Okay, sir.
enzyme. All right.
Yes.
Now,
Yes.
in fact, I have a sample of PLA which I had it now. I forgot now. I just for people, I just put it on the on the top of a plant outside in my office. Okay, all right.
Yes, sir.
Just
Yeah.
like a polyethylene goes and sits on a plant, right, on a
Yes,
on a
sir.
tree, and I put it,
Yes, sir.
and it was there for 2 years. Okay, nothing will happen.
Yes. Okay.
All right, but if the
Yeah.
same polyethylene film, if the same PLA film, I put it in a composting pit, which is maintained at 60 degrees centigrade. And you know why it's 60 degrees centigrade? The TG of PLA is about 58 degrees centigrade. Okay.
Yes, sir. Yes,
I
sir.
have
Yeah.
to take it above TG. Otherwise, the organisms don't eat a crystalline polymer. Okay.
Yeah. Yes, sir.
Okay. So I
Yeah.
have to take it above the TG. The TG of PLLA is about 55 degrees. So I have to take
Yeah.
it to 60 degrees when there is some amount of softening that occurs.
Yeah.
And that
Yeah.
softening enables, and then I need an esterase as a catalyst. Okay.
Yeah.
In order to
Yes.
hydrolyze. So I had to
Yeah.
put an esterase, which is an enzyme, and I have to maintain 50%, 55% humidity.
Yes, sir.
I need water for hydrolysis, right?
Yeah.
Only then it will degrade. So people
But
who supply these cutleries,
yeah.
I have seen in abroad also you get these cutleries, but then they have to take it to a composting environment or a company
Okay.
which composts.
Okay, sir. So
Okay.
even in India, sir, this Air Vistara, they are maintaining this kind of supply chain.
I don't know. I have no idea. You should ask them when they give it to you. Next time you travel by air with them, you ask them, where is this plastic going after I use it?
Yes, sir. Yes, sir.
You understand?
Yeah.
Because
Yes,
you see, this is the problem. Somebody has told them it is biodegradable, so they feel they are doing a service to society. Ultimately, that plastic will be thrown away in the same garbage, system where other plastics are being thrown.
Yes, sir.
So it's no use, Why do I do this, And that's what I
Yes.
said. And it comes from expensive sugar, And why
Yes.
would I want to do this,
Yeah.
So
Yes, sir.
I mean, in fact, as people, do solutions are just because of optics, Somebody wants to show that I'm using PLLA,
Yes, sir.
But you have to have the right environment, for it to biodegrade. Otherwise, the same cutlery will not biodegrade in any other environment.
Yeah. Okay. Thank you, sir. Thank you for your inputs.
Thank you. So whenever somebody says something is biodegradable, you ask this question, in under what conditions that is biodegradable, okay?
Yes, sir. Sure, sir.
Okay. And as a scientist and engineer, you should ask this question, what are the conditions of biodegradation?
Yeah.
If they don't know, that means they have not understood the problem.
So I think there is no more questions. Already time has exceeded. I would like to thank Professor Sivaram to respond many of the queries, and still if anybody is having any question and queries, you can email to the professor in later stages. Now, because already the time is over, now Professor Chattopadhyay, you just give the vote of thanks to Honorable Professor Sivaram.
Yeah, thank you, sir. It's my great pleasure. Myself, Shri, head Polymer Department, Polymer and Process Engineering Department. I feel honored and privileged to give vote of thanks for this institute lecture given by our Padma Shri Swaminathan Sivaram for this wonderful talk on sustainable polymer and its future directions. My sincere gratitude, sir, for this wonderful, informative talk that you have delivered today to all faculty, colleagues, and students who have enthusiastically participated and contributed to their curiosities and try to enlighten each other about the different facts that we are experiencing under this sustainability of polymer materials. Now, my heartfelt thanks are also due to our Honorable Director, Professor Chaturvedi, for entrusting me with this responsibility and introducing this institute lecture series through which several faculty members and students are getting enlightened with these different topics that are of future, that are giving future directions to Indian research, and hope that will help our institute and our country in the long run. My sincere thanks are due to Professor Y.S. Nagy and the Institute Lecture Series team who have taken lot of pains to arrange this whole function and giving logistic support to organize this today's lecture series by Professor Sivaram. My I would like to take this opportunity to thank all my faculty colleagues and students who have participated in this event, and I am really grateful to be a part of this event. Thank you so much, sir, for your wonderful lecture.
Thank you very much,
Thank you all.
Professor Chattopadhyay. Thanks for everyone for listening to me patiently for so long. So thank you very much.
Thank you so much, sir. Sir, actually, in fact, before I conclude, you were my examiner for my PhD thesis from IIS Bangalore. When I did, you did the PhD thesis.
With whom did you work?
I worked with Professor Giridhar Madras.
Oh,
Professor
okay.
Giridhar Madras.
Okay.
Long back in 2002.
Okay.
2002.
Very good, very good. So I always
Thank you,
like
sir.
to know that students with whom I have interacted as a student days are now in faculty position. Hopefully, one of these days when things improve, I will come and visit all of you in IIT Roorkee.
Sure, sir.
Please
Sure,
welcome, sir.
sure. Thank you, sir. Thank you so
Thank
much.
you. Bye-bye. I am now
So-
logging off.
Bye-bye.
Okay?
Thank you, sir.
Thank you, sir.
Yeah.